Okay, so last week, I introduced sequential logic, which is just digital logic that has memory. The memory is in the form of flip-flops and registers, generally. In Verilog, in System Verilog, well, in Verilog and System Verilog, there's two ways to create memory in your HDL. If you have an always block, and you have inputs inside the logic block that are treated as inputs, meaning that they're on the right-hand side of an assignment, or they're like a part of a condition that's evaluated by an if statement, or a case statement, or a for loop. But if they're not in the sensitivity list, right? So if you have inputs in the always block that are not given in the sensitivity list, that means that you have potential inputs that are not immediately going to update the output of the always block, right? Does that make sense? That will cause the compiler to create memory. It infers memory. Likewise, if you have a conditional code inside your always block that doesn't update all the possible outputs, depending on the control path taken through the conditional code, then that will also infer memory. So in other words, if you don't list all your inputs on the sensitivity list, or if you don't update all your outputs, then you will automatically get some form of memory. I mentioned last time that System Verilog formalizes this a little bit more than what you had in Verilog. In System Verilog, there's a special type of always that's specifically for creating memory, and that's the always underscore FF versus the always underscore com, which is for always underscore com, which is designed for combinational logic, whereas in Verilog you would just use an always for both. Okay, so it makes sense. So if you write Verilog that has inferred memory, then you're creating sequential logic. We looked at an example, a little counter that is technically sequential logic. It has an always underscore FF. There's generally with sequential logic, you have a clock that's in the sensitivity list, sometimes a reset as well, if you have asynchronous reset. And in this case, we just count up and down. So we have a count, which represents the state, even though this isn't designed explicitly as a finite state machine, but you still have state. You have a count as the state, and then this is determining what count gets on the next cycle. So it's like the next state logic, right? And then you have the inputs, which are enable up and enable down. This is a little hard to read because you don't know from just looking at the always statement, you can't tell right away what the inputs and outputs are, right? You have to look inside there to figure that out, right? So enable up and enable down are your inputs. Count is your output, is also the state. Okay, we also talked about a latch versus a flip-flop. Latches capture input as long as the clock is high, and then when the clock drops, then it freezes the output queue. Whereas a flip-flop is edge-triggered, so the output changes on the rising edge of the clock, or the falling edge of the clock, one of the edges of the clock. Does it make sense? So what's the deal with that? Like why the edge? Well, the idea is the principle here is that the edge, the rising edge, is supposed to be a very short amount of time. Right? If your clock cycle, which is the duty cycle, the period, from rising edge to rising edge or from falling edge to falling edge, if that's say a nanosecond, which it would be for a 1 gigahertz clock, then the rise time and fall time would be what? Would be like tens of picoseconds, right? So the idea is that when the clock rises, this is I like to think of this like as the shutter time of a camera. This is a very short amount of time that's used to open up the flip-flop for inputs, like in terms of like a camera, like expose or to capture, take a snapshot of the inputs. It happens during the very small amount of time where the clock is rising. Okay? Now, you can do latch behavior in FPGAs, but it's considered to be bad design practice. I think the reasoning behind that is because it makes timing closure difficult for the tools, which from the perspective of the programmer, it means you're going to have slow circuits, right? It's going to have a slow clock. It's best to use flip-flops. Latches, generally speaking, the only time you'll have latches is if you mess something up, if you have a bug, you made a mistake, something wrong. Okay, so we went through some examples, so you can have enables and resettable. You guys, I think this symbol, this is the standard IEEE symbol for a flip-flop. But, and the book shows these to you, but you probably didn't look at these in 211, right? But normally, if you had studied these in your digital logic design course, this symbol would mean something to you. It would imply a certain, behavior, right? And the behavior is, it's a flip-flop, it just captures values on the edge of the clock. But in Verilog allows you to write sequential logic blocks that do more than just simple D flip-flop type behavior, such as the counter that I showed earlier. So this counter has flip-flops, but they're sort of inherent inside the code of the always block. You guys with me? So when you synthesize this to the hardware, you're going to be using flip-flops. It's going to be building this on top of flip-flops. But you don't have to write your Verilog in a way where you're explicitly creating flip-flops as they do here. This is just an example. You guys with me? So in other words, you can have one always block, and you can have, like, all of the flip-flops in your design could be all in one always block if you want, right? And in addition, they could do more than just be flip-flops. They can have counters and other stuff in there too. Some can have enables, some cannot have enables. You can build that all into your always block. So don't feel as though you have to write according to this template. This is just an example. Okay. All right, so skipping ahead here. So sequential logic can be sort of ad hoc code inside an always at pause edge clock block like we had with a counter, or you could describe sequential logic more formally as a finite state machine. And so we looked at this example last week. This was a traffic light controller, and this problem lent itself well to a finite state machine type design because there's this sequence of 4 states that the intersection is in. The intersection is allowing traffic to flow on academic and stopping it on Bravado, or it's in a state where it's transitioning between academic and Bravado, where you have this yellow light on academic, and then it's in 2 more states where Bravado has traffic flowing, and another state where Bravado has a yellow light, so it's transitioning back to an academic green light. You guys with me? So there's 4 states, and they sort of sequence. You're in one state at a time, because these are deterministic finite state machines, so only one state can be active at any time, and you have this natural sequencing. And this sort of sequencing pops up a lot in digital logic design. We looked at the other example. I think I have it on here somewhere. Yeah, so this was another example. This was a controller for an elevator, and I added the solution on here. So this also had 4 states because there was 2 floors, so you could either be idle at one of the 2 floors or the elevator could be in the process of changing to the other floor. So it lent itself to having these 4 states. We also covered, for the traffic light controller, I covered the 3 pieces of a finite state machine, or any sequential logic for that matter, implementation, which is next state logic, some sort of memory bank or clocked logic, and then the output logic. So you can split sequential logic into those 3 pieces. Generally speaking, if you're designing a finite state machine in Verilog, you're going to have a separate block of code for each one of these things. So you'll generally have 3 always statements, 1 for each. You don't have to. In fact, in the example I showed at the very beginning, the counter, everything was compressed down into the one always block. So this, we had the next state logic in here, as well as the clocked logic, because this was part of an always at pause edge clock block. And then the output logic was just trivial, because the output logic was just an identity function of the state, which was the count. Bless you. You guys with me? So the three pieces are sort of conceptual. They're always there, but you don't necessarily have to put three always blocks. But usually when you look at Verilog code, there'll be at least two always blocks. You'll have one clocked and one next state. Sometimes they'll combine the next state logic and the output logic into one combinational always statement, and then the clocked will be a secondary one. Why is that? Why don't they just try to compress everything down to one block like this? It's for readability. Verilog is difficult to read as it is. It's already nearly impossible to read even well-written Verilog code, so why make it harder? So you should try to make it as explicit as possible. Yes?
So putting the enable up and down inside the if instead of putting it in an always and having it on the sensitivity list, is that the difference?
Well, if there was a sensitivity list, if there was a if there was a combinational logic block here for doing the next state logic, then you would have to have an internal variable called count next, so that guy would always generate count next as a function of count, and it would be pretty easy because count next would always be count plus one, right? And then this thing would then just have count next in here, right? Because this would be the clocked logic. So inside the pause edge clock, you would take count next and put it in a count. That would happen on every rising edge. You'd have another block that would calculate count next, which would be count plus one. That would be combinational. And then the output logic would be trivial in this case, because there's nothing, the output is literally just whatever the state is. There's no encoding between the state value and the output, right? Does that make sense? Yeah. But in this case, since it's simple, now something like this, I'm not saying that I'm not saying that this is bad. This is okay because it's so simple. But anything more complex than this, including like that traffic light controller, you'd probably want to split into three always blocks for readability, right? Okay, and then also, so part of the conceptual part of this of the class is how would you build this in gate level logic as opposed to system Verilog. So if you're actually designing this like you probably should have done in 2.11, which is to kind of draw this out as logic gates, you would have to build a next state table that would take the current state along with the inputs and then generate the next state, right? In order to do that, you would have had to find encoded values for each of the states. So normally when you draw the state diagram on paper, you have symbols, English names for the states, like idle, going up, whatever, locked on target, or whatever kind of thing you're designing. And then at some point you would have to convert, you would have to you'd have to map, each one of your state names to an encoding, and then those encodings would be how you would build the next state table, and then derive the Boolean expressions from that. Does it make sense? So I kind of went through this part pretty fast. I assume you guys are pretty comfortable with this, right? This is very similar to doing, it's really just building a truth table. But the tricky part is you have to take, what you're doing there is you're looking at all of the arrows in the state machine and you're converting that to a table, right? That's the tricky part. So when your current state is S0 and T sub A is 0, then the next state will be S1, right? You see how that works? So every one of these arrows is a line on the truth table, a row in the truth table. Make sense? So you'll have multiple rows for each state because you have multiple arrows coming out of each state, right? So in this case, we've got 1, 2, 3, 4, 5, 6 arrows, and I bet there's 6 rows in that truth table. Yep, 6 rows in the truth table. Okay? So make sure you're comfortable with that. This is kind of a way to hand build one of these state machines as opposed to writing the Verilog and having the synthesizer do it for you, right? And then the output table is in the case of a Moore machine, the outputs are a function of only the current state, and if this were a Mealy machine, then we could put the inputs in here as well. And when I say inputs, I mean the FSM inputs, meaning the traffic sensors in this case. Okay. Okay, let's look at another example. In fact, I'm going to do a live demo here, which is always asking for trouble. So here is the final exam that I gave in this class in 2016. This was back when I used to give practicum finals, where instead of it being a written final, everyone would just come into the lab and they'd have 2 hours to get a design working. So this asked you to create. This gives a bunch of specs. This is asking you to design a module called bit counter, which is a data word histogram generator. The idea, well, let's see, design a module that will examine the contents of data packets arriving through a serial single bit input stream. Each of these packets consists of a sequence of 2-bit words. Thus, there are 4 possible patterns for each 2-bit word. Your device should count the number of times each pattern occurs within each packet and output the counts of each of the 4 8-bit outputs. So you get a packet, you don't know how long the packet is. So you're getting a packet, variable length, it's comprised of 2-bit words. But the twist is that the words don't arrive as 2 bits, they arrive as 1 bit each. So you're getting 1 bit each, and you're having to deserialize those into a sequence of 2-bit values, which form the packet. While you're receiving the packet, you're keeping track of a histogram of the number of occurrences of each of those 2-bit words. So if you get a packet that comprises 8 copies of 00 and 6 copies of 01 and 3 copies of 10 and 1 copy of 11, then that would be your histogram, right? And you would just keep track of that. Does it make sense? Okay, so the module has the following inputs. You have a clock input and data, which is a 1-bit input, and there's a frame input that is asserted when you're receiving a packet, because the packet size is variable, so we need to know when we're getting a packet. And then the output, you have 4 8-bit outputs. So this limits the number of, this actually limits the packet size, right? If this means that the most number of characters of the number of symbols of each of the 4 types of symbols is limited to what you can store in an 8-bit value, which is 255, right? So this is limited to about 1,000, packet size of 1,000 at most, and that's assuming that all 4 words are equally represented. Okay, when the frame signal goes high, the module should zero the counts, the count outputs, and begin counting. The frame symbol will never be high for longer than 512 cycles. Blah 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 blah. Okay, so this is the most important thing, is the timing diagram. Shows you how it works. So we have the clock. There's the data. So it's kind of hard to see, but you know, the data is low, high, high, high. I actually also show it down here, the bits coming in. And then there's the frame that goes from low to high here and goes back to low here. So you get this first packet that comes in has 1, 2, 3, 4, 5, 6 cycles. And so it's going to receive 3 words in 6 cycles. You divide by 2. And then there's a second frame that comes in 1, 2, 3, 4, 5, 6, 7. So this is an odd number. Last one is disregarded. The last bit is disregarded if you have an odd number of cycles. And the first packet has data is 0. Oh, sorry, that's not a 0. 1. See that? 1, 0. So 1, 0 is the first word. So you can see count 1, 0 gets incremented to 1 here. And then the next word is 1, 1. So 1, 1 gets incremented here. And then the next word is 1, 0. So then 1, 0 is incremented again to 2. So by the time you get done with the first packet, you've seen 0 occurrences of 0, 0, 0 occurrences of 0, 1, 2 occurrences of 1, 0, and 1 occurrence of 1, 1. Make sense? Okay. All right. So how would we design this in System Verilog? I'll create a directory, empty directory, go into there. I'm going to call this bit counter.v. You might have noticed we had a little bit of a glitch with the, and Charles, I didn't tell you this yet, but the test bench that you guys used to test lab, I guess it was lab 1, the Verilog file name was not the same as the module name, right? But it still worked, right? Anyone have an issue with that? Okay.
Yeah, I might have forgotten.
And actually, I don't want to call it .v, I want to call it .sv, sorry. It's a force of habit because I'm been using Verilog longer than System Verilog. Okay, so you start out with module, I'm going to call it bit counter. Input, I'm going to have clock. Now, one of the things, can you all see that okay? One of the things that we used to be a little sloppy with in the past was we didn't put reset signals in all the time. I don't know if you noticed, but that lab sheet didn't say that you needed a reset. But this semester, we have to stop doing that because System Verilog will not allow you to use an initial block, which initializes memory, when you use the always _ff block. So in other words, if you use always ff, meaning that you're writing in System Verilog, the only way to initialize your memory is with a reset signal. You can't tell System Verilog to initialize it for you. You might have noticed again in our code that we gave you in Lab 1 that we did use an initial block, but we weren't using an always _ff. But in this semester, we're fully committed to switching to System Verilog. So, and that was a bad habit anyway, relying on. So anyway, we're going to add a reset signal in for this lab. So input reset, and let's see. Let me format this a bit. Does that make sense? You guys with me on this? So reset will reset to the sanity state. Okay, and then there's a there's a frame, and was it data? What was the input? Data, yeah, data frame, and then we have output logic 7 down to 0, count 0 0. Count 0 1, count 1 1, or 1 0. Not that it matters, but count 1 1. And module. Okay, and then so now this one is a little. You have to make a decision because we have counters in here, which are sequential logic, but we also need another sequential logic thing that takes care of sequencing. You know, essentially deserializing the data as it comes in. You guys with me? So there's different ways. There's lots of ways you can do this. I think that the most obvious way to do it is to create counters for each counter, and then you can have a separate state machine that tells those counters to increment or reset. You guys with me? Make sense? So I'm going to start out by I'm going to have a logic called enable count 0 0, enable count 0 1, enable count 1 0, and enable count 1 1. And I also going to have a reset count that will reset all the counters because the lab sheet, or actually the exam in this case, said that when the frame signal goes high, the module should zero the outputs. And also notice too, it's kind of subtle, but those counts, you see how the counts were kind of, there was like just a line prior to the first packet coming in? That was because those were don't knows, like they were undefined. Because there was no, this design did not reset those with the reset signal. In fact, we may not want to reset them with the reset signal because according to the behavior of this, we don't have to reset the counters until we get a frame signal, right? Okay, so, all right, so we got those, and then I'll have a always underscore FF at pause edge clock, begin, end, and I will combine all the counters into I'll combine all the counter behavior into one always block. So I'll say if enable count 0, 0, then count 0, 0 equals count 0, 0 plus 4 apostrophe B1. Okay, so notice that I have an input called enable count 0, 0. It's not part of the sensitivity list. So that is why this will become a sequential logic. This is how Verilog will know that I'm trying to create memory here. Notice also that I used the non-blocking assignment because it's sequential logic. And when I added 1 to this, I specified that the 1 was going to be 4 bits. So because this is, oh sorry, that should be 8 bits actually. Sorry, 8 bits. These are 8-bit counters. But the point is that the count 0, 0 is 8 bits, and what I'm adding is 8 bits as well. So I'm not going to rely on the compiler to figure that out. Also, notice that if enable count 0, 0 is not asserted when this always gets activated, then it will retain the old count, right? So that's kind of like having an enable signal. An enable from, if you just had a regular flip-flop with an enable. Okay, let's see. Let's see, how am I going to do the reset here? Say if reset count, then I'll have to set them all to 0. So begin count 0, 0 equals 8 B0, and then I'll reset these guys, and then I'll have an end else. Now check this out. This is something that I always thought was strange, but you have to put the begin and end for that if statement, and then you're putting the else after the end, right? It's a little different. And then I'll have to put another begin after the else. And then I'll update these. So let's count 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. Okay. And end. All right. All right, so now I've got the counters. All right, now I need the state machine. So for that, I'm going to have to draw the state diagram. And then I'll take my design and convert it to Verilog. So I'm going to assume that I have an idle state that'll be my reset. I need that because that's where I'll sit if I am not receiving a packet. If I get frame, so frame equals 1, I'm going to transition to another state where I'm going to start counting bits. The problem is that I can't count the bit until I can't count the word, can't count the occurrences of the word until I've received 2 bits. So I have to go through this intermediate state where I have to basically after I've C a 0 versus C a 1, right? No, I didn't explain that very well. So there's a state, each of these states, there's 2 states where that I would go to if I am receiving a packet, but I'm on an odd bit number. right, as opposed to an even bit number. Okay, and then, so this would be frame equals 1 and data equals 0. So if frame is 1 and data 0, I go to that state. If frame is 1 and data equals 1, I would go to the C1 state. Okay. Now, if frame is 0 and data is anything else, then I would stay in the idle. But I'm not, so there's this loop back state here that's technically there, because it would have to be in, like if you were synthesizing this, you would have to generate logic to implement that transition from idle to idle. But I'm just not showing it, on the. I mean, I wouldn't normally show it, but I'll show it here. I'll just say frame equals 0. Right? Okay. And obviously data would be a don't care. Okay, and then from here, if frame equals 0 again, and frame equals 1 rather, and data equals 0 again, then I'll go to this state that says C00. 0. And once I'm in that state, I'll enable the counter for the 00 counter, which I called enable count 00 equals 1. So again, I'm assuming that if I don't say if I don't set one of those enables to 1 or the reset to 1, it's implied to be 0, right? So, and then likewise, if I get frame equals 1 and data equals 1, then I'll go to C01 and I'll enable that counter, enable count 01. Make sense? So I'm putting the outputs inside the state, so this is a Moore machine. And these labels are just, arbitrary. So I'll have a C10 state, that's a frame equals 1 and data equals 0, and I'll have a C11 state if frame equals 1 and data equals 1. And then I'll have the enables, enable count 10 equals 1, and enable count 11 equals 1. Make sense? So now what? Well, once I get into one of those states, I have to decide where to go next. If the frame signal is held high, then I'll have to continue looking at bits. So if the frame signal is held high, then I'm going to go back to one of these intermediate states where I've seen an odd number of bits, right? So for example, if I have frame equals 1 and data equals 0, then I'll go back to C0. Right? Make sense? Right? Likewise, if I say frame equals 1 and data equals 1, then I'll go back to C1. So I'll go back to either this state or this state from either one of those. Or for that matter, same thing from these guys as well.
When you reach the C and then like the 0, 0, 0, 1 state, you say that your counter is equal to 1. Is that just like short for like you're adding 1 to it?
No, I'm not looking at the counters directly. I'm only enabling the counters here.
Gotcha.
Right. So I'm just looking at the data, and I am keeping track of whether I'm on an even number bit or an odd number bit. If I hit an even number bit, I want to know, you create essentially this tree type structure that will match any of the, in this case, 4 patterns. And these are non-overlapping, so it's odd, even, odd, even, odd, even as I receive bits. And so whenever I reach one of these 4 states where I've received an even number of bits, then I know whether the last 2 were, what the last 2 bits were, I enable the corresponding counter. And then the counters will do their own, they'll operate concurrently with this always block. Right? And then the other thing I haven't shown is that if frame drops to 0 when I'm in any of these states, then I want to go back to idle, right? But there's a problem with that, because the way it's described, when you go from having a frame to not have to the frame ending, so after receiving a packet, you want to maintain your counts until you get the next packet. So you don't want to reset the counters until you start receiving a new packet, right? Make sense? So where do I reset the counters? Well, I can't actually do it in one of these 2 states, because I keep returning to these states even while I'm receiving the current packet, right? So there's a couple options. I could add a reset state, reset counts here, that goes back to idle. So for example, if I get a frame equals 0 from any of these guys, I can go back to here, in which case I'll reset the counts to 0. That's an option. Or I could just, that's probably the best way to do it, actually. So just have everyone come here. The problem with this, though, is you run into a problem, because what happens if the frame is low for only 1 cycle between 2 packets? See, that'll cause a problem, because I have to go through 2 states to get back to idle. There's a 2 cycle delay before I can reset everything. You guys with me? Right? So how to solve that? Well, I can solve that by allowing a new packet to start while I'm in this reset. Right? I could draw additional transitions from this back to these 2 guys if I happen to start a new packet right away. Make sense? So I think that's the way to go. I think that's the easiest way to do it. Okay, so first thing is I need a state type. So type def enum logic. How many bits do I need for how many states do I have here? 1, 2, 3, 4, 5, 6, 7, 8. Oh, good. So 3 bits. So 2 down to 0. State type, and then sorry, I have to go and check. I always forget the syntax for that. You put the states before this. Okay, right. So I got to go back over here and say idle, resetting, C0, C1, C00, C01, C10, C11. So how many states is that? I count right. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. And then I need to have state type for current state and next state. And then I need my clock logic, so always _ff at pause edge clock. I'm also going to make, I'm going to put a pause edge reset in here as well. I'm going to make this an asynchronous reset. And I'll do if reset, then current state equals idle, else current state is assigned to next state. Good? Everyone agree with that? Okay. So this is nice because, this will only activate on the rising edge of one of these things. So if this activates and reset is not asserted, that means that the clock must have been the thing that activated it, and we must be on a rising edge, right? Okay, and then always comb, begin, end. So now I need my next state logic. Okay, so now this is where you have to choose how you want to set this up. In some cases, it's easiest to use a case statement for this, right? You can have one case for each state, each current state. Or you could do an if-then-else block. It's up to you. I think in this case, I think I'm going to use an if-then-else because there's some redundancy in here. If I'm in either one of these states, C0 or C1, my next state logic is the same. They both have exactly the same transitions coming out of them, right? Likewise, all four of these guys have the same transitions coming out of them. So I'm going to compress things down a bit. I'm going to take a shortcut. Because otherwise this would be pretty long. So I'm going to say if current state equals C1 or current state equals C1, then I'll say if frame and data, not data, then next state. Now I'm going to use a blocking assignment statement here because this is combinational logic. So it's just single equals, not less than equals, just equals. The next state is going to be C. Oh, wait a minute. Hold on. No, I screwed that up. I can't combine these together. All right, that's all right. I'll keep them separate. So if I'm in C0 and I get another 0, then I got to go to C00, right? Else, if frame and data, the next state equals C01. Else, if not frame, then next state equals, and this is where I'm gonna, in this case, this would only happen if I get an odd number of bits. You guys with me? Because I've seen, at this point, I'm in the state where I've seen a 0 as the odd bit, but frame has dropped. So my packet has ended before I receive an even number of bits. And that's okay. I'll just ignore it. It won't, nothing will get, none of the counters will get incremented. But I have to go, back to idle. And
Rest, right?
actually, you know what? I got that wrong. Yeah, no, I don't want to go back to, I want to go, let's see, if I go back to, you know what? No, I screwed that up. Scratch that. I made that more complicated than it needs to be. I can just go back to idle from all these guys. Right? I don't have to go through the reset because I don't want to reset when I end the frame. I want to reset when I begin the new frame. Make sense? You guys with me? Like it said that when I start a new packet, I want to reset my counters, right? So I don't need to go back into a reset state. So I'm just going to go straight back to idle. I'm going to go straight back to the beginning. Okay. Else if current, let's see, actually I'm going to just copy and paste this now.
Trevor, where do you reset the counters then in your state machine?
Yeah, I need to update that actually. I think the best way to do that would be, I had it reversed. I had them resetting when I finished the packet. Who asked that? Was that you? Yeah. I had them, the way I had this drawn is when you finish the packet it would reset, but in fact I want to reset when I begin a new packet. So I'll actually have to create, I guess the easiest way to do that would be to create a reset version of these two guys. Right? Yeah, so I can have, so in other words, the first time I pass through these states, I will reset. On subsequent trips back, I'll go to these two ones that don't reset, right? So I'll have like a shadow of each of those two. Or I can cheat, and I can just delay the frame signal by one cycle. I don't want to, I'm tempted to do it that way, but that's really kind of a hacky way to do it. So another way to do it would be to have a delayed form of the frame. If I have a delayed copy of the frame signal that reflects whatever the frame was in the previous cycle, then all I have to do is reset my counters whenever the old frame was 0 and the current frame is 1, right? That will allow me to detect a rising transition of frame, right? A better way to do it would be to have the shadow copies of this. I think. Yeah, that's the problem. It would induce a delay. So if you did it that way, the first bit would be ignored. Yeah. Right? You'd miss the first bit because you were busy resetting. Now, the way to get around that is to have the shadow, the different, like a version of C0 and C1 that will reset the counters and at the same time keep track of the first bit. Right? It's just going to add more states. That's all. Let's see. I'll be lazy and I'll do it the other way. Inside this always underscore FF. So I'm going to add some additional logic here. So in addition to this being my, oh man, now Charles would never approve of this. This is so sloppy. All right, I'm going to create another always block. I'm going to create another always block specifically for delaying the frame signal. Yeah, that other way was way too hacky. So I'm going to have a pause edge clock, and I'm just going to say frame last is assigned to frame. There you go. So now I have frame last is whatever, that's a delayed version of frame. And so I will create a logic for frame last there, right? So I added a frame last signal, and I just set that to whatever frame is whenever the clock edge happens, meaning that whatever time I'm in, I can look at frame last, and it's like looking back in time to what frame was in the previous cycle. So, okay. So
you have a cycle to do your initialization, right?
Yeah, but I will reset everything. But see, I have one reset. So the main reset that comes in, which is scrolled off the screen, the main reset. So the main reset is going to reset my controller, but not the counters. I'm going to allow the counters to come up in an undefined state because the way it's described, I only want to reset my counters when I start a new packet, right? So the frame is essentially going to serve as the resetting mechanism for the counters, right? So I'm not going to use that reset for the counters. Why? Because I have to reset the counters between. I want to count the number of words in each packet. So in between packets, I want to reset that, and I won't be getting a reset signal, right, for that. Okay, so and I can actually, in addition to creating that little delay logic, I'll also do an always underscore com, and I'll go ahead and just set reset. What do I call that? Reset count is going to be. Actually, I don't even need a. Why am I doing always for that? I'm just doing a assign statement. Assign. Reset count to be 1. Sorry, I want to say when frame underscore last equals 0 and frame underscore, or just frame, equals 1b1. So, and now I have a question mark. Whoops, I don't want to end that yet. Question mark 1b1, colon 1B0. So this is a ternary operator that will check to see the condition is, I should use parentheses there. You don't need parentheses because the ternary operator has the lowest precedence of any other operator. But just to be clear, I'm going to add parentheses so I can differentiate my condition from the values that I'm setting. So when frame last is 0 and frame is 1, that means that I have a transition, right? So notice that this will be happening concurrently with the state machine, right? So that way, the first time I pass through one of these states, that logic will be operating concurrently to reset my counters the first time I go through one of these two states when I start a new packet, right? So this demonstrates, concurrency. Yes?
So it not only works because it takes 2 clock cycles to get a full input, right? Like if it was only 1, it would lag behind and you would reset after taking in the first one, right?
Not necessarily. Even if it was 1, I could reset.
Yeah, but wouldn't that be
No, you're right, because it would be 1. Yeah, you wouldn't have time
to reset that?
to reset, yeah.
So you could just reset after, as soon as you get a frame in 0,
Yeah.
because you wouldn't need that.
Yeah, that's a good point. Yeah, so what he's saying is that if we were doing if we received 2 bits per cycle as opposed to 1 bit per cycle, then there would be no time to do this reset. Okay, all right. So I've got my reset stuff in there. Okay, so back to the state machine. So if I'm in C0, then I will go to C00 or C01. Otherwise, I'll go back to idle. And then let's see. Okay, so I'll do begin here and end because otherwise it's confusing. All right, if so I'm going to put that there and I'll add the end back and say else. If current state equals C1, then I'll change these guys. There you go. So if I'm in C0 and I get a 0, I go to C00. If I'm in C0 and I get a 1, I go to Z01. And then if I'm in C1, it's the same thing except that first bit is different. Okay. Okay, now I think at this point I can take advantage of the redundancy in those states. So I'm going to say end else if current state equals C00 or current state equals C01 or current state equals C10 or current state equals C11. Now you might say, wait a second, how can you treat all those states the same? I mean, you're doing different stuff. You're incrementing a different counter depending on which state you're in. Yes, but that's part of the output logic. I'm not doing output logic. This is the next state logic. As far as the next state logic is concerned, it doesn't matter which of those states I'm in. At least I don't think so. We'll see. Yeah, so I'm going to have a single if statement here. So I'm going to paste that down there. And I'll just take off the prefix. There you go. So if I'm in any of the sort of the leaf states where I increment a counter, then I'm just going to go back to C0 or C1 or back to idle if I end the frame. And likewise, that even applies to, come to think of it, that also applies to the idle state, right? So even if I'm in the current state equals idle, then I will also do the same thing. Any questions? So if I'm in idle or any of these guys, then my next state logic is identical. I'm always going to go back to one of those 2 odd states. odd numbered bit states. And I think I'm done here, right? I think that's all the states. 1, 2, 3, 4, 5, 6. Yeah, I only have 7 states now. Oh yeah, so I can also go back and delete that resetting state as well. Okay. All right. End. Hopefully that's right. Yep. All right, and then I'm going to create my output logic, which is always comb, begin, end. Oh, I need another end here. No, I've got it. Yeah, I'm good. I should be good. Okay, so I'm going to do my output logic. I'm going to create some default outputs. So I am going to, by default, I'm not going to increment anything. So enable count 0, 0 is 0. And as well as the other 3. So all my enables will be 0 by default. But if current state equals C00, then I'll set enable count 00 to be 1.
Why are your enable bits 2 bits?
The enables are, oh, sorry, you're right. They shouldn't be. It should be 1 bit. Thank you. Okay, and then I'll take care of the other 3. All right, there's my output logic. I think we're done. Okay, so the reset count is set there. Clock logic is here. Counters are here. Next state logic is here. Output logic is there. I think we're good. All right, now it's time to see if it compiles. Okay, got an error. Undefined variable enable count 0, 1. Must be enable count 0, 1. Did I not name it?
In the logic, you put CN instead of EN.
Oh, that was just that one. It was that one typo. Okay. CN was, sorry. Line 7. Oh, it was when I declared it. Oh, okay, thank you. There we go. Yep, thank you. Okay, and then we've got line 31. Unexpected assignment. Oh, sorry, when you do an assign, see, that's a syntax thing. So when you do a continuous assignment statement in Verilog, there's just a 1 equal sign. I always forget that because in VHDL, the equivalent statement in VHDL is called a concurrent assignment statement. It does exactly the same thing, but it uses the less than equal thing. So I always screw that up. Okay, 47, unexpected end. Okay, I was worried about that. So I think the reason why we're getting that is because I was a little, oh, that was 47. Well, that end was supposed to be end this always comb.
I think you're missing a begin on the last also.
Yes, thank you. Excellent. That would have taken me a little while to figure that out. Begin, there we go. All right. Okay, there we go. They're compiled. Now I've got back when I used to do practicum final exams, I would give everybody a do file or a test bench that would test their design. In this case, I have a do file, which I think I've got here somewhere. Yeah. Okay. So check this out. Here's this is a do file, by the way, is just a script for Model Sim. This one starts out by setting up the waveform window for everybody. So that way you could run the do file and it would set up the waveform window so you could directly compare what you got with that. So if everything worked, you should get exactly what's shown on here. And that includes, notice that this has these dividers where it says inputs and outputs, so I divide up the inputs and outputs. And also the amount of time it's run for, and the zoom was all set up in the do file. So add wave just adds the waves. There's also, you can add a divider that just adds a dummy divider. And then this statement, wave restore zoom, sets the zoom. And then we restart. And then this command will tell ModelSim to set up a clock signal, which you can do in a test bench with an always block, as we showed you as well. And then this thing, went through the reset cycle and stuff. And then it sent the same sequence of data. So let's see if it works. So I'll do vsim-no vopt bit counter. Okay, looks good. I can see my signals in there. And to run the do file, you just type do exam.do. And go to the wave window. All right, looks good. So I got my, sorry. Actually, I need to reset the zoom. So I'm gonna hit this little magnifying glass to reset the zoom. The do file didn't originally have the reset in it, and once I added the reset, it made it run a little longer than originally had it set up for. So there's our clock. There's the reset pulse that happens at the beginning. There's the data inputs and the frame inputs. You can see the two frames. There's one packet. There's another packet. The first packet is 1, 2, 3, 4. 1, 2, 3, 4, 5. 5? 1, 2, 3, 4, 5, 6. Sorry, 6 cycles. And yeah, because that one has an even number, and then this one is 1, 2, 3, 4, 5, 6, 7. So that has an odd number of cycles. The first frame has if you look at data, and you look at frames. So from the time frame goes high, I get a 1, 0, a 1, 1, and a 1, 0. So 1, 0 gets incremented to 2, and 1, 1 gets incremented to 1. Looks good so far. Now the problem is if this hadn't worked, you'd be kind of lost because there's not much to tell from this. So I am going to add in the other signals just in case I needed to debug this, which you can access over here. In fact, I'm just going to do a right click on this thing and say add wave. It'll add them all. So here's all the other signals. Now notice it doesn't show, it only shows the values of the signals that were plotted when I ran this the first time. So I'm going to have to rerun it to recover the new signals. I'm also going to delete the ones I already had. Okay, so I'm going to do, I'm going to restart the simulation, and then do exam.do. Now one of the problems with using a do file is that because the do file adds all the waves, now I've got it added all the waves again, so I have to delete them. All right, so you see from here, let me change size of the column that shows the signals so we can read them. Okay, so you can see I've got current state and next state, and also I've got the frame last signal, which records whatever the frame was. So if you look at frame last, in fact, if I drag frame down next to frame last, or actually I'm going to bring frame last up to where frame is. Notice how frame last is a delayed version of frame. They're the same signal, it's just this one's been phase shifted by one cycle to the right. Right? And so that way, remember the logic it looked at when frame was 0, sorry, when frame last was 0 and frame was 1. So that cycle matches the condition to reset the counters, and then notice that the counters get reset in the following cycle, right? You guys with me? Also, the other thing that I wanted to point out is that when my current state becomes C10, I'm supposed to be incrementing the 10 counter, right? Which I do. There's the enable for that right there. You see that pulse? But notice that the counter, the 10 counter, doesn't actually get incremented till the next cycle. See how there's a delay? Right? So I'm in the 10, I see 10, I tell it to increment, there's my increment signal, the enable, but it takes a cycle for that to update, right? Because it's a register. The counter's a register. When you have a register, there's always a delay of one cycle to change it. Okay? Any questions about that? Okay, great. All right, so okay, so the last thing I wanted to talk about in this chapter, or this lecture, this topic, was timing. Remember that model sim shows you a behavioral simulation. This is only for functionality. If you make this circuit on an FPGA or an ASIC or with TTL logic chips or however you build this circuit physically, you're not going to see instantaneous changes between, like, from the clock edge to when that clock goes high, that's what's causing frame last to change. But according to this, it happens exactly at the same time. You don't see that there's a causal relationship between the clock and frame last because there's no delay there, right? In reality, you'd have propagation delay. It would respond to the rising edge, but it wouldn't happen. You wouldn't see frame last go high immediately. Likewise, the next state logic. Remember that the current state, or the next state, is calculated from the current state, but according to this, the next state changes at the same time the current state does. So the current state changes, the next state changes immediately, right? I mean, if you don't believe me, I can zoom in. That's the zoom in active cursor. So I'll just, wait, where's my active? Oh, did that not work? There's my active cursor. Zoom in on active cursor. Yeah, it should be zooming in. No, it's not working, huh? Zooming in at the end. Okay, well, let's do it this way then. I'll zoom in a bunch of times, and you see on this, I don't know if you can notice that, you see that in the back. You see it shows the cursor, even once I zoom in to where I'm zoomed in, the cursor's off screen, it still shows it on the scroll bar down there, so I can still find it. There it is. Okay, so this is in picoseconds. Yeah, it happens, well, wait, where's the transition? I lost the transition, didn't I? There it is. There's the transition. Yeah, so you can see I can keep zooming in and zooming in. I'm still, you'll never see a delay. Yeah, that's the most I can zoom in. You're never going to see a delay here, right? It's instant. But in reality, there's a delay. There's delays, there's logic delays, and even the flip-flops have delays. In addition to having delays, flip-flops have timing requirements. You have to have the input coming into a flip-flop. So one of the things I mentioned, let me back up here a second. One of the things I referenced earlier was the reason why we use the clock edge to activate a flip-flop is because the rising edge of the clock is a really short amount of time, right? Right? But, and that is when you actually lock in the input into the flip-flop, is during the rising clock edge. But the flip-flop circuit requires that the input to the flip-flop, the D input, it has to be stable for a certain amount of time before the clock edge happens. is called the setup time. And it also, the input to the flip-flop has to also remain stable for a certain amount of time after the edge. That's called the hold time. You probably didn't, I'm sure you didn't cover that in 211, setup and hold time. The setup time plus the hold time is the time period around the rising edge of the clock, which together refers to is called the aperture time, which comes back to the camera metaphor that I referenced earlier. They call it the aperture time, right? So you might say, well, who cares? Like, how does that affect us? Yeah, there it is. There's a picture of it. So you've got the clock edge, and then the D. Remember, D is the standard name for an input to a flip-flop or a register. Setup is, you have to be stable for the setup time, and you have to remain stable after the hold time, which together, that's TA, that's the aperture time. If you don't, if for whatever reason you change the input within a setup T setup of the clock edge or within T hold after the clock edge, if you change it within T setup before the clock edge or within T hold after the clock edge, then the flip-flop could become metastable. It goes in, what it does is it goes into a, the Q output will go to some value between 0 and 1. And it won't stay there forever. It'll eventually settle on whatever value it was supposed to be, the correct value. But it will go into this metastable state where there will be a time period where the output will be undefined. It'll be sort of between 0 and 1. You'll capture it'll capture sort of an in-between state. And so you want to avoid that. Now you might say, well, how do you avoid that? What can we do? What can we do to prevent this from happening? The setup time is, the way that you don't violate the setup time is by setting your clock period long enough such that you guarantee that all of the inputs to all of the flip-flops in your design will arrive in plenty of time before the clock edge, right? So in other words, you have to have a long enough clock period. Make sense? So if your setup time is violated, it means you're running the clock too fast. The hold time, on the other hand, is a little bit more nuanced. The hold time doesn't have anything to do with the clock at all. It has to do with not having any paths from an output of a flip-flop to an input of another flip-flop that doesn't have enough delay in it. Right? So in order to, you can fix the hold time pretty easy. If you can identify paths in your circuit that violate hold time constraints, all you got to do to fix it is to put in dummy buffers, like you put in logic gates that don't do anything, they just add delay. You guys with me? Make sense? Okay, so let's look at some examples of that. First of all, let's define a few things. So there's remember we talked about propagation and contamination delay, but we talked about those in terms of logic gates. Flip-flops also have propagation and contamination delay. So with the logic gate, typically you have T sub C is the contamination delay, and T sub P is the propagation delay, right? With a flip-flop, it's T CCQ for contamination and T PCQ. You guys follow that? I never could follow that because I don't know what the C stands for in there. I get the C and the P are contamination propagation, and I get the Q because the Q is the output of a flip-flop, but I don't know what that middle C is on either one of those terms. Never. Maybe clock, but it's not really. Maybe, yeah, it could be. Yeah, that could be. Yeah, that's a good guess. Okay, so not violating setup and hold times is called dynamic discipline. So the idea is that generally speaking, you're going to have flip-flop output through logic generates an input into another flip-flop. Now you might say, wait a second, that's not how the design that you just made in Verilog didn't work that way. It did actually, but it didn't have two flip-flops here. In that case, when you do next state function, you have The state, which is the output of a flip-flop, goes through the next state logic and comes back into the input of that same flip-flop to create the next state, right? It's a feedback loop, right? So this doesn't have to be two separate. What I'm trying to say is, even though this picture shows two separate flip-flops, it doesn't have to be two flip-flops. It could be one flip-flop that has a loop back. It doesn't matter. The point is that you have outputs of flip-flops that feed the inputs through logic. And so then you have TC, which is the clock period. That's rising edge to rising edge or falling edge to falling edge. However you want to, it doesn't matter. It's the same thing. And then the contamination delay is just like with the logic gates. That's when the output of a flip-flop begins to change after the clock edge. And the propagation delay is how long it takes to settle into its final value. Now these are technology parameters. These come from the spec sheet of your flip-flops or your FPGA, right? This is not something you have any control of. This is this is inherent to the technology. This is something that improves with Moore's law, by the way. These things get better with better semiconductor technology. Well, they used to anyway. Not so much anymore. But this is a Moore's law thing. But this is a function of the semiconductor. Okay, so what about these constraints I was talking about? Like, so how do you guarantee you don't violate the setup or hold time? Well, I mentioned it's actually pretty simple. It has to do with the clock period. The clock period has to be long enough to accommodate three things. Well, at least three things. The propagation delay of the flip-flop, the propagation delay of the logic between the flip-flops, and the propagation delay of, the setup time, which is the slack, the amount of time you have to have your input stabilized before the clock edge, right? Make sense? It's cushion. You have to be stabilized for this amount of time before the clock edge in order not to change within the aperture. Okay? Make sense? Now remember that this TPD propagation delay is the worst case propagation delay. It comes from the critical path of the circuit. So you're going to have, remember, logic circuits don't necessarily have the same delay through them from the inputs to the outputs, right? So there's the notion of a critical path, which is the longest delay path through the circuit, and that's what you base your propagation delay on. It's the worst case delay. And so that's your constraint, but it's written another way. They take propagation delay and they isolate that on one side of the inequality, and they move the TPQ and the T setup to the other side of the inequality. Why? Because the assumption there is that we can't control those. We can't control this. We can't control the propagation delay of a flip-flop. We can't control the setup time for the flip-flop. That's given to us by the chip maker. And usually you can't control the clock period either, because you're designing, the assumption is that you're designing for a certain clock period, right? So the thing that you can control as the synthesizer, or as the compiler, as the entity that generates the hardware, is the propagation delay. You guys with me? So the idea is you design one circuit. If the propagation delay is too high, you violate this, and you got to go back and do something to change the propagation delay. Hold time is, as I mentioned, is not dependent on the clock, but you have to make sure that the hold time is less than the contamination delay of the flip-flop plus the contamination delay of the logic. And again, that contamination delay is the fastest possible path through the logic circuit. So this is the opposite of the propagation delay. You have to look for the shortest path. You guys with me? Right? So when you put the contamination delay by itself, it's saying the contamination delay must be greater than these things, meaning that you may have to increase that. You don't want to be too low. You don't want your contamination delay to be too low. All right, so here's an example. This is the kind of, the typical example. Here's a circuit. You get some timing characteristics. So the contamination delay of the flip-flops is 30 picoseconds. The propagation delay is 50 picoseconds. Right? So meaning on the clock edge, you know that things will start to change at 30 picoseconds, and they'll stabilize at 50. So there's a 20 picosecond time when things will be in flux, right? The output. Then the setup time is 60 picoseconds, and the hold time is 70 picoseconds. So these all come from our flip-flop spec sheets. Also, the per gate in the logic, the propagation delay is 35 and the contamination delay is 25, right? So the first question is, do we meet the setup time constraint? Well, to answer that, we have to find the critical path so we can calculate the propagation delay of all the logic. The critical path is going through up to how many gates? 3, right? Worst case delay is I have to go through all 3 gates. I come into this gate, through that gate, and that gate. So my propagation delay is 3 times the propagation delay of a single gate. So it's 3 times 35, it's 105 picoseconds. The contamination delay is the shortest path through here, which would be through this gate, and so then you're subject to the contamination delay of a single gate, which is 25 picoseconds, right? So this is the propagation and contamination delay of your logic. The setup time from the equation given on the previous slide says that the clock period must be greater than or equal to the propagation delay of the flip-flop, which is 50, the propagation delay of the logic, which is 105, based on the critical path, and the setup time, which is 60, right? So that means that the maximum clock, that adds up to 215 picoseconds, which defines your smallest clock period, right? And so if you take the reciprocal of that, you get 4.65 gigahertz. Any questions about that? Make sense? Okay, and then the hold time says that if you add up the contamination delay of the flip-flops and the logic, which is 30 here, logic is 25 here, that's 55, is it greater than the hold time for the flip-flops, which is 70, and answer is no. So this circuit won't work. So how do we fix it? It's actually pretty easy. We can add buffers to slow this down. So notice they added a buffer here, right? I get that, right? Because that's the shortest path, right? They also added a buffer to the second shortest path. Why?
To wait for the input of the first one?
No, you don't necessarily have to balance these guys. No, I think it's not shown here, but I would bet that if you measured, the contamination delay we measured for the logic was just this gate, right, which was 25, right? But even if you added a buffer here, right, then and you didn't add one here, then your critical path would either be going through that buffer and that gate, or through this gate and that gate, right? And so that might have still violated the whole time, but actually it wouldn't have, because in this case all of the
That's for your output.
Like C to X.
Oh, sorry. Yes, thank you. Yeah, you're right. That's right. Thank you. Good catch. Yeah, right. So where I was wrong was the shortest path wasn't just this guy, because there was this other path from C to X. You're right. Yeah, because you had a 1 gate delay from D to Y and C to X. Yeah, that's right. Thank you. Yeah. All right. So yeah, so we added the two gates. So they recheck that, and it works out, because it changes the logic contamination delay to 50, right? Yeah, so 30 plus 50 is greater than 70. Yep. Okay, but that's not the whole story, because there's also clock skew that you have to worry about. Because the analysis that we did before assumes that the clock edges that every flip-flop on the chip sees the clock edge at the same time. And that's not true because the clock signal comes into your chip and it propagates out to all the flip-flops, but it takes time from where the clock comes in to, depending on how far away the flip-flop is from the source of the clock. You guys with me? Because the clock network on a chip has a lot of metal in it, has a lot of capacitance. It takes time to charge it. And you'll see that clock edge arrive at different times on different parts of the chip. That's called clock skew. So in order for, now, modern FPGA tools, as far as I know, don't estimate the clock skew at different parts of the chip. They always go by worst case clock skew. So basically they look at how long, what is the maximum clock skew you'll get anywhere on your chip, and they'll calculate all the timing paths based on that. Which is, you might think, well, that's kind of pessimistic, isn't it? Yeah, and that's why I used to overclock my FPGAs all the time. Because they always base these timing constraints on the worst case. Not only worst case for clock skew, and the clock skew is going to depend on where you map each one of your flip-flops, like how you allocate the resources on the FPGA. Clock skew may be worse if I map two connected things far apart versus closer together. But the tools always use the worst case. But also, the clock skew also depends on the temperature of the FPGA when you're running it, because the semiconductors behave differently depending on what temperature they're at. Generally speaking, delays get worse with hotter chips, right? So if you look at the FPGA tools, they will use the 100 degrees Celsius as they use all the delays that you would get at 100. Like, so in other words, they always calculate delays as if you were operating the FPGA in an oven, essentially. Again, another reason why you can usually safely overclock. Anyway, so how do you account for clock skew? It's really easy. You add that as the fourth term to the setup time equation. Inequality, technically. So, it's a bound. So the clock has to account for this skew. Right? Now you may say, well, why are you just adding it to that? Well, that's because what the clock skew means is, the clock skew means that you may have a clock period, depending on what path you're considering, you're exercising on the circuit, on the chip. The clock period may appear shorter than it actually is because of the skew. You guys with me? So if I'm running the clock at 5 gigahertz, so 200 picoseconds, 200 picoseconds is edge to edge, assuming no skew. But if you have skew, you may the effective clock period may be shorter because I may be generating output from a register that's on one spot on the FPGA and reading it from another spot on the FPGA or ASIC. And because of the skew, the difference in when the clock signal arrives at those two places, the clock period may appear shorter. So you have to consider the skew. You have to build in a cushion for the skew in there as well. So you have to add the skew. Well, what about the contamination delay? Okay, this is the one that always confuses me. The contamination / hold time. Okay, so what this one means is, this one you have to add the skew to the hold time, meaning that you may have to hold it longer. You may have to hold the signal longer because the signal coming into your flip-flop may be generated by another flip-flop who had its edge even longer ago than the clock period. You guys with me? So when you look at propagation delay, you're worried about the skew compressing the clock cycle. But when you look at hold time, you have to similarly consider the fact that the skew may be lengthening the clock cycle, in which case in which case data coming into my D input may change sooner than I expected it to because it was generated from another flip-flop whose cycle was farther away, whose clock edge was farther away than the clock period. You guys with me? Make sense? So if you add the contamination delay of the flip-flop plus that of the logic, it has to be greater than the hold time plus an extra cushion for the skew.